Hello friends, today we are going to start a new series of lectures on electricity and magnetism. We are all the time surrounded by devices that depend on the physics of electromagnetism, which is the combination of electric and magnetic phenomena. For example, this physics is at the root of computers, television, radio, telecommunications, household lighting, and even the ability of food wrap to cling to a container. This physics is also the basis of the natural world. Not only does it hold together all the atoms and molecules in the world, it also produces lightning and rainbows. In today's and some of the following lectures, we shall distinguish between electrically neutral, negatively charged and positively charged particles and identify excess charge. Distinguish between conductors, non-conductors, semiconductors and superconductors. Describe the electrical properties of the particles inside an atom. Identify conduction electrons and explain their role in making a conducting object negatively or positively charged. Identify what is meant by electrically isolated and by grounding. Explain how a charged object can set up induced charge in a second object, and identify that charges with the same electrical sign repel each other and those with opposite electrical signs attract each other. Origin of electromagnetism. Electromagnetism was first studied by the Greeks, who discovered that if a piece of amber is rubbed and then brought near bits of straw, the straw will jump to the amber. We now know that the attraction between amber and straw is due to an electric force. The Greek philosophers also discovered that if a magnet is brought near bits of iron, the iron will jump to the magnet. We now know that the attraction between magnet and iron is due to a magnetic force. From these modest origins with the Greek philosophers, the sciences of electricity and magnetism developed separately for centuries until 1820, in fact, when Hans Christian found a connection between them. An electric current in a wire can deflect a magnetic compass needle. While preparing for an evening lecture on 21st April 1820, Hans Christian made a surprising observation. As he was setting up his materials, he noticed a compass needle deflected from magnetic north when the electric current from the battery he was using was switched on and off. This deflection convinced him that magnetic fields radiate from all sides of a wire carrying an electric current, just as light and heat do. And then it confirmed a direct relationship between electricity and magnetism. The new science of electromagnetism was developed further by workers in many countries. One of the best was Michael Faraday, a truly gifted experimenter with a talent for physical intuition and visualization. In the mid-19th century, James Clerk Maxwell put Faraday's ideas into mathematical form, introduced many new ideas of his own, and put electromagnetism on a sound theoretical basis. We begin our discussion on electromagnetism with electrical phenomena, and our first step is to discuss the nature of electric charge and electric force. Electric charge. These two demonstrations here will prove the presence of electric charge. After rubbing a glass rod with a silk cloth, we hang the rod by means of a thread tied around its center. Then we rub a second glass rod with a silk cloth and bring it near the hanging rod. The hanging rod magically moves away. We can see that a force repels it from the second rod. But how? There is no contact with the rod, no breeze to push on it, and no sound wave to disturb it. In the second demonstration, we replace the second rod with plastic rod that has been rubbed with fur. This time, the hanging rod moves towards the nearby rod. Like the repulsion, this attraction occurs without any contact or obvious communication between the rods. In our discussions, we shall surely discuss how the hanging rod knows of the presence of the other rods. But first, let's focus on just the forces that are involved. In the first demonstration, the force on the hanging rod was repulsive, and in the second, it was attractive. After a great many investigations, scientists figured out that the forces in these types of demonstrations are due to the electric charge that we set up on the rods when they are in contact with silk or fur. Electric charge is an intrinsic property of the fundamental particles that make up objects such as the rods, silk and fur. That is, charge is property that comes automatically with those particles wherever they exist. Types of charges. There are two types of electric charge, a positive charge and a negative charge, denoted using algebraic signs. In most everyday objects such as a mug, there are about equal number of negatively charged particles and positively charged particles, and so the net charge is 0. The charge is said to be balanced and the object is said to be electrically neutral or just neutral for short. Excess charge. Normally, you are approximately neutral. However, during winters in North India, when the humidity is low, the charge on your body can become slightly unbalanced when you walk across certain carpets, sit on plastic chairs, and even sometimes when you wear certain kind of jackets. In such situations, you either gain negative charge or you lose negative charge and become positively charged. Either way, the extra charge is said to be an excess charge. You probably don't notice it until you reach for a door handle or another person. Then, if your excess charge is enough, a spark leaps between you and the other object, eliminating your excess charge. Such sparking can be annoying and even somewhat painful. Such charging and discharging does not happen in humid conditions because the water in the air neutralizes your excess charge about as fast as you acquire it. Two of the grand mysteries in physics are: why does the universe have particles with electric charge? What is it really? And why does electric charge come in two types and not say one type or three types? We just do not know. Nevertheless, with lots of experiments similar to our two demonstrations, scientists discovered that particles with the same sign of electrical charge repel each other and particles with opposite signs attract each other. We shall surely prove this rule in quantitative form as Coulomb's law of electrostatic force between charged particles. But before that, we need to understand the motions of the rods. The term electrostatic is used to emphasize that relative to each other, the charges are either stationary or moving only very slowly. When we rub the glass rod with a silk cloth in a less humid conditions, a small amount of negative charge moves from the rod to the silk, a transfer like that between you and a carpet or the chair, leaving the rod with a small amount of excessive positive charge. We rub the silk over the rod to increase the number of contact points and thus the amount of transferred charge. We hang the rod from the thread so as to electrically isolate it from the surroundings, so that the surroundings cannot neutralize the rod by giving it enough negative charge to rebalance its charge. When we rub the second rod with the silk cloth, it too becomes positively charged. So when we bring it near the first rod, the two rods repel each other. Next, when we rub the plastic rod with fur, it gains excessive negative charge from the fur. When we bring the plastic rod with negative charge near the hanging glass rod with positive charge, the rods are attracted to each other. All this is subtle. You cannot see the change or its transfer, only we can see the results. Conductors and insulators. We can classify materials generally according to the ability of charge to move through them. Conductors are materials through which charge can move rather freely. Examples include metals such as copper in common lamp wire, the human body, and tap water. Non-conductors, also called insulators, are materials through which charge cannot move freely. Examples include rubber, such as the insulation on common lamp wire, plastic, glass, and chemically pure water. Semiconductors are materials that are intermediate between conductors and insulators. Examples include silicon and germanium in computer chips. Superconductors are materials that are perfect conductors, allowing charge to move without any hindrance. In our discussion, we shall only be dealing with conductors and insulators. Conducting path. Here is an example of how conduction can eliminate excess charge on an object. If you rub a copper rod with wool, charge is transferred from the wool to the rod. However, if you are holding the rod while also touching a water tap, you cannot charge the rod in spite of the transfer. The reason is that you, the rod, and the water tap are all conductors connected via the plumbing to Earth's surface, which is a huge conductor. Because the excess charge put on the rod by the wool repel one another, they move away from one another by moving first through the rod, then through you, and then through the water tap and plumbing to reach Earth's surface, where they can spread out. The process leaves the rod electrically neutral, in thus setting up a pathway of conductors between an object and Earth's surface. We are said to ground the object, and in neutralizing the object by eliminating an unbalanced positive or negative charge, we are said to discharge the object. If instead of holding the copper rod in your hand, you hold it by an insulating handle, you eliminate the conducting path to Earth, and the rod can then be charged by rubbing, as long as you do not touch it directly with your hand. Charged particles. The properties of conductors and insulators are due to the structure and electrical nature of atoms. Atoms consist of positively charged protons, negatively charged electrons, and electrically neutral neutrons. The protons and neutrons are packed tightly together in a central nucleus. The charge of a single electron and that of a single proton have the same magnitude but are opposite in sign. Hence, an electrically neutral atom contains equal numbers of electrons and protons. Electrons are held near the nucleus because they have the electrical sign opposite that of the protons in the nucleus and thus are attracted to the nucleus. Were this not true, there would be no atoms and thus no you. When atoms of a conductor like copper come together to form the solid, some of their outermost and so most loosely held electrons become free to wander about within the solid, leaving behind positively charged atoms or positive ions. We call the mobile electrons conduction electrons. There are few, if any, free electrons in a non-conductor. Induced charge. This experiment here demonstrates the mobility of charge in a conductor. A negatively charged plastic rod will attract either end of an isolated neutral copper rod. What happens is that many of the conduction electrons in the closer end of the copper rod are repelled by the negative charge on the plastic rod. Some of the conduction electrons move to the far end of the copper rod, leaving the near end depleted in electrons and thus with an unbalanced positive charge. This positive charge is attracted to the negative charge in the plastic rod. Although the copper rod is still neutral, it is said to have an induced charge, which means that some of its positive and negative charges have been separated due to the presence of a nearby charge. Similarly, if a positively charged glass rod is brought near one end of a neutral copper rod, induced charge is again set up in the neutral copper rod, but now the near end gains conduction electrons, becomes negatively charged and is attracted to the glass rod, while the far end is positively charged. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. The strength of a particle's electrical interaction with objects around it depends on its electric charge, usually represented as Q, which can be either positive or negative. Particles with the same sign of charge repel each other, and particles with opposite signs of charge attract each other. An object with equal amounts of the two kinds of charge is electrically neutral, whereas one with an imbalance is electrically charged and has an excess charge. Conductors are materials in which a significant number of electrons are free to move. The charged particles in non-conductors, that is insulators, are not free to move. So friends, that is it for today. In the next lecture, we shall be discussing the Coulomb's law and the electrostatic forces acting between particles. Thank you very much.